There we go. Okay, welcome everybody. We are pleased to have Dr. Brown here with us from Stanford University uh, for the STEM Education Seminar of Fall 2022. Dr. Brown comes to us, as I mentioned, from Stanford University currently. I have a very special connection with Dr. Brown, and that is, he doesn't know about this, and that is that he is a former high school biology teacher, and so am I. I taught high school biology for 14 years, so that I want to emphasize that connection. But then Dr. Brown went on to earn a master's degree in educational psychology from University of California, and then a PhD in educational psychology from University of California in Santa Barbara. And after a postdoc at Michigan State, he is now working as a faculty at Stanford University. In science education, his main line of research has to do with urban science education, and especially the cultural contexts in urban science education. And as is evident from the title of his talk, the intersection of race and language and culture with science teaching and learning. So without further ado, now I turn it over to you, Dr. Brown. Please take it away from here.
All right, well, thank you for having me. And I know it's late in the afternoon, and so I know that's particularly challenging. So be patient with me as we work through it. So I'm going to offer a basic premise, kind of a halo for our discussion today. And that when we think about classrooms, there is something that I want to introduce to you called the lingua culture. And lingua culture comes from the work of Dr. Michael Agar, who's a social linguist. And the idea is that every culture has a language, and let me say it the other way, every language has a culture. So the question is, what is the language culture of the science classroom? Let me give you an example. We've all gone to Starbucks. I've yet to meet a person who's never gone to Starbucks. And there's a very powerful and peculiar thing that they do. I go in and I say, can I have a small coffee? You know the response. They say, absolutely. So you want a grande. They revoice the coffee. I never asked for a grande, but they never tell me I'm wrong. They very politely correct me. It's an amazing systematic training that they do because I've noticed it over the years. So there's a culture dynamic. They are very vigilant about naming their drinks a particular name and creating a particular culture, right? So what is the lingua culture of a science classroom? And this was striking for me when I was a high school teacher in Southern California, because I would enter a conversation and say, inside of the cell is the nucleus, and inside of the nucleus is organelles, and inside of the organelles, one of the organelles or ribosomes make protein. And the kids' eyes would glaze over, and they're looking at me like, what the heck are you talking about, right? I came across a study many years ago from Dale Baker that said there are as many new words in an introductory biology class as there are in an introductory Spanish class. But if that is the case, we have lots of new ideas, we have lots of new language, then the question is, what's the lingua culture of a classroom? And here's the sad part. When I walk into a biology classroom, the one thing I don't know is biology. When I walk into a chemistry classroom, the one thing I don't know is chemistry. I walk into a physics classroom, let me just save you the message here. I also don't know the chemistry. Then the teacher asked me a whole bunch of questions about the one thing that I don't know, and they expect me to answer with the correct answers. So the language culture doesn't make sense, if that makes sense. So here we go. Also, learning is multidimensional. It's psychological, it's cognitive, and social. So here's what I mean. From a psychological standpoint, studies by Claude Steele around stereotype threat that most people are familiar with, or Valerie Perdue-Vaughn's around social identity contingencies. And to be brief about what that means is if I have any doubt about whether or not I'm supposed to be there, it raises my anxiety. So think about it. If I'm a student who is questioning, am I really supposed to be in this science classroom? And then I have just been introduced to a wealth of new ideas and new language. What does that do to the psychological positionality of students? Many
Dr. Brown, may I interrupt? I'm
Please
really
do.
sorry, but I don't know whether this has to do with my Zoom meeting or from your slide. We're seeing this gray box on the screen. Are you seeing that also? as you are sharing your.
I don't see it. Let me change the share. I think I may have a solution for it.
It's kind of hiding part of your slide, actually.
All right. How about now? How are we doing now?
We have smaller gray boxes near the top now. Now they're gone.
Is that good? Okay.
Yeah, yeah, that's
So
good.
those
Thank
are
you.
those
Sorry
are
for
the boxes.
interruption.
No worries. Those are the boxes where the images of you were, the picture. So I don't see you.
Oh, I see. Okay.
But no worries. So to get to the point, there are psychological components. So a lot of people can tell you about growth mindset, but I want to argue that there's another subsection of those that deal with the teaching and learning of science. Think about our discipline. What other discipline do you say, well, you know, you're not talented enough to learn English. You're not smart enough to be an excellent history student. They don't make those claims, but we're quite comfortable arguing that science is the realm of the elite. So there's a psychological component. There's also a cognitive component we're going to talk a lot about today, which is, are we teaching in a way that people learn? And lastly, social. Are we engaged? What do the people around me suggest? Those of you in classrooms, are you in a place where students believe that being a scientist is a feasible option? It's something that I should consider. If not, I want to make the claim that all three of these pieces, the psychological, the cognitive, and social, play a role in learning. So quickly, this is not a rhetorical question. I'm going to need your help. I'm going to ask you to put this in the chat. These are phones. For those of you who do not know, both of these are phones. Some of you have never seen that thing on the left that spins around. There was a time when I remembered everybody's phone number. Now, this is no joke. Every friend, every family member, I remembered them. I deleted all phone numbers except for one or two. Here's the question. I'm asking you to put this in the chat. Why is it that we deleted these phone numbers? So do me a favor, write it in the chat. Why do we no longer remember phone numbers? I'm going to stop my share so I can see your comments. All right, technology does it for us. Good. We don't need to know them anymore. Good. Because we don't have to. Well, I would argue smartphones, they did a lot of really powerful things. And one of the things they did is made remembering things unnecessary. For example, remembering phone numbers are no longer necessary. I'm going to also argue if you have a sibling, you may remember that number, or you have a parent, whatever your holy crap, I'm in trouble phone number is, you know that one. That is the one that you remember. So here's the argument. Value creates necessity for learning, right? And it is repetition and use. It's the number you probably use most often, and it is the number that is most valuable. So repetition equals retention, and it has the highest value. But here's the bad news. Every class your students go into, someone is going to tell them this is super important information you need to learn. That's history, that's English, that's math, that's science. So how is that possible? How are they going to remember all the information if these computers on our shoulders do a fabulous job of deleting information? Many of you may remember MapQuest. You printed the direction, they gave you turn by turn. I'm making a point. We've experienced a subtle revolution where the technology in the palm of our hands has caused us to delete any unused information. So from a cognitive perspective, are we teaching in a way where students are able to use the information that they see on a day-to-day basis? Because here's what I know, they will delete all unused information, right? So this is not new information. Vygotsky warned us about this. He called it constructivism. He didn't do it, but in retrospect, he was talking about zones of proximal development and how we connect new ideas to existing ones. And so the question in science learning is, when we're teaching, are we teaching in a way where students can see the phenomena in their lives? Because again, they're going to delete all unused information. Even more recent adaptation of that perspective comes from the work of Ellerby Brown and Campion. There are scholars and learning scientists who talk about situated learning theory. The idea is that the information we acquire is more useful than the information that we're learning. And here's the distinction. If I have to learn the content in pursuit of learning and doing something, I'm more likely to master it. And here's a simple analogy. There's a phrase in the carpentry community, and that phrase is, we measure twice and we cut once. And here's what I know. Everyone I know who is a carpenter who works in that industry, they're phenomenal at adding fractions. Not that they went to fraction class, but building a chair, framing a door, framing the concrete pour requires you to learn and deal with fractions at a level where the mastery becomes important. And so this is what situated learning theory suggests. We want to teach in an authentic context where there's social interactions that we're working together to explain, to analyze, to build. and we want to connect it to meaningful tasks. If we do that, then we won't delete that information. So the argument here is if learning is psychological, if it is cognitive, it is social, we have to be careful to teach it in a way that people are going to learn, and that means situating science in meaningful context. Here's why: they're going to delete it anyway. So from a cognitive perspective, we also know this work. The work of Brenda Fonseca and Mickey Chi for over 20 years, they did this work on the self-explanation effect. And many of you are familiar with the ICAP framework. And the argument is that the least effective mode of learning is literally what I'm doing right now. I'm blabbering, you're listening, right? So passive learning is the least efficient mode of learning, where something like reading a text would be passive. The next in the hierarchy of efficiency is active learning. And this is the idea of me trying to copy notes or say back, write back what I'm hearing, right? So that is active. Constructive, I am now making my own meaning out of it. So I am revoicing, explaining in my own words what's happening. This is the third in the hierarchy. It's also called the self-explanation effect. And you know, as a teacher, the moment you had to rethink it, to teach it to young people, you really had to master it. And this is constructive learning, kind of the revoicing. The highest in the hierarchy of ICAP is interactive learning, where the group of us, 2 or 3 of us working together, have to make an explanation, construct an analysis, taking information and working on it is the most efficient. And so to save you years and years of reading, if you dive into the work of Dr. Mickey Chi, who's right there, not so far from you in Arizona State University, what they found is that study after study after study, those who are taught in a mechanism which enables them to construct their own explanation, meaning they have to explain it to someone else or write it and explain it to themselves, and have greater retention. So the question is, are we teaching students in a way that really is mastering learning? Now, let me give you some practical examples. So if I'm thinking about hydrogen bonding, right? Traditionally, we talk about weak electrostatic forces, right? I learned years ago that if a person was to straighten their hair, if their hair was curly, or if their hair was curly, I messed that up. If their hair was curly and they straightened it, or if their hair was straightened and it was curly, I'm trying to figure this out, but I think you know where I'm headed. Curly hair made straight, straight hair made curly. Either way, if you alter your hair, what you are altering is bonding structures, right? So if it is humid outside, I know that's not a big deal in Arizona, but in most places, lots of water, lots of humidity, what happens is the polar nature of the bonds breaks the bonds of the hair, so the hair gets frizzy again, right? So the reason why you want to teach in this context is every time that young person walks into a humid room, it is like them dialing that phone number again, an opportunity to use that scientific information. So hydrogen bonding in the context of hair texture is a powerful way to make sure we go from I don't know it to I master the content, to I use it regularly, right? Similarly, if we're talking about the concept of mitosis, I apologize for the biology examples. I'm a biologist by discipline, so I tend to stay in this realm. But I can teach mitosis by having students learn about how programmed cell death is supposed to happen, why we have breast cancer, and promoting breast cancer awareness as a way to understand what's happening mitotically in our cells. Is I'm actually teaching things that as students come across regularly, they now have expertise. So the question is, are we teaching in a way that students are learning? One of the things that happened here at Stanford many years ago is there was a study to show that there was a serpentinite rock that was interacting with bacteria, and you had a redox reaction was making the mercury, it was causing mercury bioaccumulation in the water. And so through a simple redox reaction, you started to see bioaccumulation and presence of mercury. So as people ate tuna, right, they were consuming high levels of mercury. And so they put out a national warning to say for pregnant women, we need to avoid tuna for this very reason. So why would I not teach the concept of redox reactions in the context of preparing and making sure people were safe in their pregnancies? And the reason why, every time a young person encounters someone who's in pregnancy, I want them to think, okay, let me make sure I'm communicating. We want to make the scientific information knowledgeable, right? So with that said, I want to now switch to our third domain. We talked about cognitively, our students explaining. We talked about the social dynamics of feeling stressed out, being uncomfortable, and whether or not I'm creating spaces where students are engaged in authentic science. But what about the language? I want to set this up really quickly. This is an interview from, I believe, the 2013 National Championship football game. This gentleman, Jameis Winston, throws a touchdown, they win the game, and he's asked a question, and here is his response.
15 to go in this game. Final drive. What did you tell your teammates around you?
I said, guys, we didn't come here for no reason. I said, guys, this is ours, man. This is all the adversity we went through. The first few quarters, it was ours to take. And like I was just saying, we control our own destiny. And those men looked me in my eye and they said, we got this, Jameis. And I said, are you strong? They said, I'm strong if you strong. And I said, we strong, man.
After struggling through the first half, what was the biggest adjustment you guys made at halftime?
We had to go back to playing Florida State football. We came out here, we were letting us be bigger than the game. We were bigger than the game. Then we had to say, hey, let's play Florida State football because can't nobody be bigger than this game. And we did that, and we came out victorious.
All right. Now, I know this seems a little bit left, but I'm going somewhere. So immediately following this interview, Dee McCarron says, am I listening to English? So this is also an awesome way for me to use Twitter for research purposes. So Dee McCarron, who is the mother of Alabama quarterback AJ McCarron, she tweets this. Now, why this is interesting, look at the date. It is January 7th, 2014, 12:09 a.m. She tweets, am I listening to English? All right. Then immediately, so we're talking minutes later, about an hour later, 1:39 a.m., she says, anyone that knows our family knows that we are far from racist. My tweet was not in any way meant that way. I sincerely apologize if I offended anyone. So apparently she got some feedback. She wanted to clarify herself. She offered this. Now, that part is not interesting to me. Here's what's interesting. Reggie Bush says, love listening to this dude, Jameis Winston, talk after games, walks and talks like a true champion, a role model for kids to look up to. So who's Reggie Bush? Former USC football player, NFL football player, 10-12. So literally it's like 3 minutes difference. At the same time, she hears it, he hears it. They have completely different perspectives. And there's another one, somebody named LeBron James, not quite sure who that is, says this, unfreaking believable interview by Jameis. Just shows part of the reason why he's so special. So LeBron James reads it the same way as Reggie Bush did. How does one person hear? This is a phenomenal response to a question. Another person says, I speak in English, right? So I'm making the point that this goes back to language culture. We don't have rules for language. So for example, why are people raising their hand to speak in your class? Who made that rule? What does it improve? Why do we sustain that mode of language culture? What does it accomplish? So here's what's clear to me. There's a word I don't like, and here's the word, organic. People use it wrong. They talk about organic fruits and vegetables. Well, to me, I took chemistry. I thought anything that had a carbon-based structure was organic. And so every kind of fruit is organic. What they're saying is leave it alone, don't touch it. I'm arguing we have not touched or challenged the way that language happens in our classrooms. We allow it to be undefined. So here's what happens when it's undefined. She can expect him to sound like a news broadcaster. They can expect him to sound like something else. Now, by context, here's a young man, 19 years old, from Mobile, Alabama, the quarterback at Florida State University in the Southeast. He plays with a bunch of young men, basically 19 to 22-year-olds who are also from the Southeast. So he sounded like a young man from the Southeast who's speaking to other young men from the Southeast. What should he have sounded like? Imagine that same interview. She says, how did you feel after the game? He says, well, it was a fascinating competition. We lost our focus midway through the competition. And our coach, he asked us to refocus. We were able to do that and we're champions. It just didn't sound right? He sounded like his family. He sounded like his community. We default to the culture of power. We want our young people to sound like scientists, but we are never clear that that's the expectation. So let me say this differently. If I show up in a science class and I have science wisdom, I have science knowledge, will I be speaking like a scientist or will I speak like a kid from Northern Arizona? Will I speak like I grew up in Flagstaff or will I speak like I am a science professor? And more importantly, what is the language culture of your classroom? If I'm listening for the right answer, communicated in correct science language, that means only people who already know are able to speak. The irony is the cognitive scientists say, I have to speak more in order for me to master the information. So what is the rule of your classroom? Are you looking for the right answers? And are you looking for the right answers to be communicated in science language? That is at the heart of the problem. We all know this, right? So in the movie Ferris Bueller, Ben Stein asked a question. He literally asked 18 questions. He answers all 18 questions by himself. So at no point is the conversation at all about what the students know. It's about him spewing information. We are so deeply ingrained in the language culture of science that we often call teaching lecturing. Like there is no difference. Because what I know is the more I lecture, the less they learn. The more they talk, the greater they learn. As a teacher, I was told good management is keeping your kids quiet. That is absolutely not the case, right? So I've been studying this for a while. We call it the language identity dilemma, and there's two components. The first is cognitive, and it's very simple. I don't understand what is being explained. We often communicate new ideas in new language, fundamentally ensuring that our young people are not going to get it. I don't understand. Secondly, students may have brilliance. They might have the right answer, but it is explained in a language practice that the teacher is not listening for. There's a failure to be understood, right? Third, language is also communicating positions and identities and who we are. So if someone is talking to me, you've all experienced this, with a great deal of jargon, I'm frustrated. That tells me I'm not supposed to be here. It sends a psychological message that students should not be here. So I don't speak like this and I should not be here. So this language identity dilemma is one of the things we've studied in our lab, and we're really trying to get people to understand just how powerful language is as you rethink your language culture. I want an environment where all young people are able to speak, where we value the wrong answer, as it is the first step towards mastery. Let me give you another example. So many years ago, I studied a baseball team in Northern California. And what I was looking for is what language of mastery existed in this context. And so for those of you who don't know, curveball curves because of the spin producing an air differential on top and bottom of the ball. So as you throw the ball, that dark red arrow, the air on top of the ball is going the opposite direction of the spin, but the air on the bottom of the ball is going the same direction of the spin. So what you do is you create an air pressure differential. It is no different than what you do with drag on a spoiler of a car or lift on the airplane. You're creating greater air pressure on one side or the other. In this case, the air pressure is greater on the top, it causes the ball to dive. This is called the Magnus effect, right? So the question was for young people, how does a curveball curve? I'm just going to play one excerpt for you.
Well, when you flick the ball, it cuts through the air. It has different airs under it and over it, and starts pressing it down, so it drops, and the air on the bottom is more loose in the right way, and it just the heavy pressure makes it drop.
All right, so I have a question for the chat. Very simple, not a rhetorical question. I really want to know: is he right or is he wrong? All right, one person says right. We got, I don't know, not sure, good. I think he's right, but we need to read it again. I will share it, certainly. Sounds right to me. All right, we're non-committal today. Okay, I know, no worries, no pressure. I'm gonna share my screen. And this, I don't trust binary questions either. So if it's right or wrong, I'm always going to look for the alternative. So who knows if he's right or wrong? All right? And more importantly, who cares? What I want is for us to be able to recognize the brilliance of his answer as the predecessor, the stage one, to getting him to mastery. So he says, when you flick the ball, it cuts through the air. It has different airs under it and over it. Now, if he means there's nitrogen on top and there's carbon dioxide on the bottom, we have a problem. If he means the air is pushing harder on top and then on the bottom, you might understand it. It starts pressing it down, so the ball drops, and the air on the bottom is more loose in the right way. So it depends on what he means by loose in the right way. The heavy pressure makes it drop. So all I'm asking is that we hear the brilliance of this young person, that we don't set up a false expectation, that we're not saying, I expect you, as you're learning, to master this new idea and the new language that I have not taught you. I want you to say that is brilliant. When you say air on top and the bottom, what do you mean? I want to create a language culture where students know that in order for me to master this, I need to explain it. Because here's what happens when I try to explain something. I recognize, I know it, I'm confident. Oh, I have no idea, which is a good place to be. Now I know what I need to know. Or I know this part, but this other part I don't know. which is also a great place to be. But how often do we enable our young people to explain the idea as the first stage, right? If you want a book to read, check out John Feldman's Grading for Equity. He talks about how when we add points to assessments, they don't really become learning tools anymore, right? It's only about points. I want us to recognize the brilliance of this young person. Recognize that we are going to go somewhere as long as we start with recognizing that the language he's using is more than enough to get us started. So I want to suggest that, this is not something we just talked about theoretically. I'm a researcher by training, by disciplines, my job. And so we developed a teaching approach called disaggregate instruction, very simple, that we wanted to disaggregate the learning of the concept and the learning of the technical language. And so the idea was start with introducing science ideas in simple language that the students know. And we used our pre-assessments to figure out what that might be, teach them the content in the context, and then we teach them and give them lots of practice using the science language. And so that's disaggregate instruction. Idea first, make sure that we're teaching an authentic context, and then give them lots of opportunities to explain, but enable them to practice using new science words. So here's an example of what disaggregating the concept might look like. So this is a teacher planning a lesson on osmosis. They figured out a context, and the context is when we have fish, assuming our kids have pet fish, why wouldn't we keep a freshwater fish in a saltwater tank, right? So here's the lesson, here's the context. Listen very carefully for how this is disaggregated. You will hear very little in the way of science language, but the idea will be expressed.
Now, we all know and love the story of Finding Nemo. Father and son get separated. Son makes new friends in a fish tank. Father goes on an epic journey to save his only child. And, following the Disney way of life, everyone ends up living happily ever after. But what if there was some dark twist lurking in the shadow of the story? What if the dentist who found our tiny orange friend actually gave Nemo to his crazy niece Darla? She doesn't know about marine life, and instead of putting Nemo into a new and friendly saltwater fish tank, she put Nemo into a freshwater fish bowl. Would it really matter? Saltwater, freshwater, it's all water, right? Would everything end up happily ever after for our little lost clownfish Nemo? No, no way. So what gives? Why can't you put a saltwater fish into a freshwater tank? Well, fish that live in the ocean, like our little friend Nemo, are happy campers when they're surrounded by water. There's salt inside Nemo's body and outside Nemo's body. And nature likes everything to be balanced. And this is exactly what happens for saltwater fish when they're in a saltwater environment. Because again, there's salt on both sides of Nemo's skin. But when you put a fish like Nemo into freshwater, the conditions around him change. Now, unlike his happy home in the ocean, Nemo has more salt in his body than the freshwater around him. Nature hates that there's more salt on the inside than on the outside and wants to balance this out. Now, if we could look through a microscope at Nemo's body, we would see that there's tiny openings in his skin, kind of like doorways. Now, the salt molecules inside Nemo's body are way too big to fit through these tiny doorways. But water molecules are super small and fit perfectly through them. Only water can move easily in and out of a fish's body. Nature wants everything to even out, and the only way you can balance this is for water to start pouring into Nemo's body. Well, Nemo has so much salt compared to the fresh water surrounding him that the water just keeps coming in his body. With this effect, Nemo may as well have been a blowfish instead of a clownfish, because he will swell up like a balloon. Eventually, he'll swell up so much that his cells will start to burst, until finally, he goes belly up. Poor Nemo. Doesn't really make for a very good Disney ending. This process of water flowing through these tiny doorways is called osmosis, and it's an amazing phenomenon. Don't put Nemo into a freshwater tank. He's a saltwater fish and needs to be surrounded by salt. The most important tip for our fishy friends out there, stay on osmosis' good side.
So to give you context, that is an exercise that we give our teacher ed candidates here in science education on disaggregate instruction. So tell me the story in 3 minutes or less of some phenomena and remove all the science language. So you can learn to start with the simple ideas and then teach the language second. And so we then ran a series of experiments. I'm just going to share a couple to document how students learned when taught with this approach. So group one was our control condition. We assume teachers don't just walk in the room and start blabbering. Most of us, like when I was a teacher, we use prefixes and suffixes to really try to embed some version of language learning, but it all happened at the same time. So I'm talking about enzymes, and I'm saying, well, anything that ends in ASC is an enzyme. So I would help students by trying to use suffixes and prefixes. And so we assumed that the control group is science and language at the same time. Experimental group is everyday language first, science second, right? So we have two groups. Both groups got a pretest. One group was taught with science and language at the same time. That's our control group. The other was taught with everyday language first, science language practices second, and then we gave them a post test, right? So the question is, does complex science language impact student science learning? Well, when you try to do a classroom experiment, those of you who do classroom work, you know it's very difficult because you have to account for teacher skill. To remove that factor, we created an online learning platform where we had the exact same software. The only thing that changed was the language. So for example, oxygen, photons, carbon dioxide versus good air that all living things breathe, light, water, and all of these had voiceover. So the students didn't need to read it, they just heard it. And so you either got this language or simpler language. So what happened? So the simplest way to explain it is across all measures, students who are taught with simple language outperform those who are taught with the complex language on all measures. And so you have different types of measures here, multiple choice questions. So overall in the multiple choice, we saw a gain of about 70% for those taught with everyday language first versus about 58% for those who were taught with both at the same time. We have two versions of questions, disaggregate questions where we ask the language in simple language, or aggregate questions where we asked with more complex language. And so if you look where it says multiple choice disaggregate, so these are when the language was simple, when the students understand, we had a huge difference there. And I want you to know, when we asked the questions using complex science question, that difference was smaller. So overall, what you'll notice that language is still an issue. Where we found the most profound difference is on open-ended questions. So when we asked them just to explain, what is the role of the stomata? You look on the right, the overall questions, when we asked open-ended questions, we saw about 30% gain for those in the treatment group to only about 16% for those in the control group. And regardless of the question type, what we found is that those who were taught with everyday language first retained information at a higher rate on all measures. So we did this again, but this time, same condition, two groups, one group simple language, other group complex language, but then I gave them site measures to see if there were any stressors involved. And so literally there was a picture and it was me reading the voiceover, and one version said evaporation happens when water changes its shape. Here's the other version. When water evaporates, it expands its bond length and changes it to gaseous form. Same image, one exact same number of words. The experimental group got simpler words. The control group got complex words. Now, there were two tests, the Stroop test and the flanker test. I got to go quick, so I'll try to make sure it's clear. In the Stroop measure, you're trying to match the color of the word, not what it says. So if the word yellow is written in yellow, you hit Y. But if the word yellow is written in blue, now they're incongruent, right? I have to ignore what it says and hit the B button because the color is blue. Similarly, the flanker test is the arrow indicator. What I'm looking for is what direction is the centermost arrow. And you'll notice here, the centermost arrow is going the opposite direction. So it's a distractor. I need to ignore the direction of the others and identify the centermost arrow. So that's called an incongruent task. And so again, the treatment group on mean, 1,300 milliseconds compared to the control group. So those taught with simple language in the Stroop measure, this is about colors. When the colors were incorrect, they were much faster, statistically significant, our effect size of 0.7, in being able to recognize the color difference. So what does that mean? That means it literally takes more cognitive capacity. These are used as stress measures for students to learn, and so they are slower in their pattern performance. So think about it. You watch a video, and immediately following this video, there are remnant cognitive factors. the best way to explain it is like parallel parking. If you're parallel parking and your music is loud, you can still parallel park, but how many times do you turn the music down simply so you can focus? So what we found is across all measures, consistently, whether it be the flanker test or the Stroop test, that students taught with simple language show faster cognitive performance. So the simple way to put it is, as students are learning science, if they're learning science with new language, right, it literally, they learn less and it produces stress-like responses. It increases their cognitive load. So why is that important? It's because I want everybody to learn. So we did find one factor, right? So we ran our regressions, and the one factor that is predictive is if you are older. So age has a predictive factor, is that students who are older tend to be faster, and the negative impacts of language don't impact them as much, right? So this is an indication. You can see the downward slope for the relationship between the control and treatment group, is that as you age, you learn to manage this language stress. So simple recommendations. If language culture is a problem, which is I'm arguing, right? We need to make sure our language culture, the environment we set up in our learning environments, produces learning. A couple things. We need to be explicit about language learning. The students need to know that what you're actually doing is learning new ideas and new language, new symbol systems. So let's make sure we're teaching language. Secondly, let's create formative assessment tasks so that they can apply the new language. The biggest mistake we're making is you don't have an opportunity to explain the idea until you get to the test. And as I mentioned before, if you get to a test, you recognize I understand this and I don't understand that, or I understand these parts, that should happen earlier. So we want to create lots of opportunities for students to explain without negative consequence. Third, let's rethink our language assumptions, please. We value the wrong answer. We need to value the wrong answer. We need to be able to use multiple language practices, which we call translanguaging. Adopt a fluency approach. Spanish teachers are phenomenal at this. They will say, you know what we're doing? No one is speaking English now for the next 30 minutes. Everyone is speaking Spanish, because speaking broken Spanish is how you become fluent. I need us all to adopt a language-centered approach to science teaching. All right, so thinking about this, if we deleted phone numbers, which is pretty impressive, well, how the heck did we retain all those phone numbers without actually trying to do so, right? And for sake of time, I want to make sure that the answer is pretty simple, is when we got that bad message that boop, 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 when we got it wrong, it cost us something. It cost us a quarter, or we had to engage in the process of going back, writing it down, explaining it. How many times as a young person, for those of you who are of age, you said the number over and over and over again, right? So that you wouldn't lose it. You remember and valued it because you got a chance to use the science. Did I say science? I meant to say you use the number in context. It had value. I want to argue that's something you have to do moving forward. A way to do that is an approach that we teach called the cognitive apprenticeship lesson planning approach. So in every lesson, we start by establishing a problem. So we teach science in the context of a problem. We switch where now we're engaged in teacher-centered instruction, where the teacher is really helping the students. Then you switch to coaching, where students have lots of opportunities to explain with your support. And finally, the third part of the lesson is fading, making sure your students have tons of opportunities to explain their ideas thoroughly. Let me give you a quick example before we close. So when I think about osmosis, I think about something like marinating meat. Right? Does it actually work? And so I might start by saying, why do we marinate carne asada? Why do we marinate chicken? Does it actually work? All I'm trying to do is teach them osmosis in a context that they will see and see again, right? So we may start by making sure they're introduced to the ideas of osmosis. So have them do a small lab, watch a video, and apply it to the notions of carne asada and marinade. So in the coaching phase, maybe I have them draw a model, right? So if the chicken is porous and the seasonings are of different sizes, show me how the water and the season are moving across. Let's do an inquiry lab. Let's actually then do a marinating task so we can actually test whether or not it works or not. And then in fading, we need lots of opportunities. So maybe we do a recipe guide for our families. Students are preparing videos to explain this concept. We need to make sure that we're actually providing a lot of opportunities to explain in context, right? Let's make small changes. So a few small recommendations you can make. Make sure your big ideas for your lesson include things that students are going to see. When we can talk about macromolecules, but let's embed it in the conversation that people are having. So maybe you're talking about the role of COVID and macromolecules in food consumption and how the way that we eat impacted so many people across the country. Change your essential questions. The second thing, formative assessment, as I mentioned before, one of the things you can do is giving your students lots of opportunities to talk about the science prior to an assessment where you're teaching both language and concept. And the last thing, let's take an action-based summative assessment approach. When they're explaining concepts, let's make them build something to explain what they're doing. Let's have them go to City Hall and make a presentation. Let's have them think critically about how the science matters through authentic tasks, because that is how we learn language anyway, by explaining to others. The last thing I'll say is technology is your tool. We have so many tools. It is a window, not a wall, to separate people. It enables them to get information, share information. The students master features all the time. Let's tap into this untapped tool and enable it to be a great learning resource for every student. I'm going to close by saying, I hope this is the first of many conversations. I'm happy to tap in with you all some other time. I'm trying to be more active on Twitter, so if you have questions, I'm happy to answer them there. But I think that the big idea is that we need to rethink the language culture of our classroom environment so we can maximize learning. You already know enough to do it. It's just a matter of being creative and tapping into what you already know. So I look forward to your questions, and thank you for having me.
Thank you very much, Dr. Brown. That was very inspiring. I would just some mechanical things. When you have a question, please raise your hand, the electronic hand, and I will invite you to ask your question. Or you can also type in your question in the chat, and I will monitor the chat and then read out your question and let Dr. Brown answer the question. So the floor is open now for people to ask questions, either by raising hand or by typing. Let's see. I'm not seeing any hands yet. There is a question in the chat. Do you have some examples of schools or teachers who are doing this well?
Not really. I mean, we do this for our teacher ed program. And so I see examples from the teachers we trained over the years, but it's not like an entire department of people doing this. Selena Gray, who is a professor at Mount St. Mary's College, who's also a science teacher, is probably the person who is most prolific at this kind of teaching. And so I've seen her, this is kind of her practice, but I don't know specifically of a place I can point you.
Thank you. Another question in the chat is, any examples in informal learning spaces with a wide range of learners, like age, demographics, etc.?
Yeah, it's a good question. So, I mean, most of this work, I'm a classroom-based researcher, so anything that I do is formal. It's in mostly middle and high school, courses. But every principle that we talked about is a fundamental learning principle. So they transfer. So the idea that having an opportunity to explain that work is done both informally and formally. So I know that the San Francisco Exploratorium was set up in a way where in its informal space, there are two different types of tasks. One where students are active, running around, playing around, and then at the margins, assuming that the students will get tired, they will sit, listen, and interact. It was designed with intention. And so the point is that everything I've shared today are vetted learning principles that should transfer to informal environments. The question about, do I have examples? No, because this is not the scholarship that I do directly.
Mm-hmm. Thank you. Next question here. Towards the end of your presentation, you mentioned using technology. What are some ideas that you might have to implement that into the classroom?
So I'm a huge fan of technological resources in changing the language culture right now. For example, when I ask teachers, we're actually doing this study right now. When I ask teachers, what did they want to keep from COVID or distance learning? Many of them said, well, when I asked students to write in the chat, many more students would participate. So when you talk about language culture, the technology is the change agent for language culture. So I like, in particular, Nearpod and Pear Deck, but Nearpod is my favorite because I can have students log in and they're now anonymous. So I can say, okay, tell me where you've seen water moving in and out of things. And so I can read real time every student's response. So I can get 30 kids to share at the same time. What I love about it is I can create authentic pressure because I can say, okay, we can't move on until I get 100% participation. So on the screen, it'll show me who's logged in and who hasn't. So if the learning theory is correct, that those who explain and get an opportunity to correct and iterate, they'll learn more. Then the technology should be able to give us a really powerful way to maximize engagement. So instead of me having to be that confident kid who will raise my hand and share the answer, I have now created an opportunity for all 30 to be able to explain at the same time, and no consequences for getting it wrong. So if you build a healthy language culture where the kids are not like messing around too much because it's anonymous, I think there's some real opportunities there.
Thank you. Next question. Have you disaggregated by demographics? We are trying to better engage Black and Latinx learners in science education.
Yeah, all of my studies are done in Northern California classrooms where almost 50% of the kids were Latino students and African-American students. And so the data is in these diverse multilingual classrooms, and the learning gains are uniform. And so if you check out any of those manuscripts, they're multilingual students who perform really well. And I mean, it's a low threshold, right? Because what we're arguing is if one condition is not teaching language at all, and the other condition is saying, here's the idea and the word, if I'm a language learner, then of course, it's a much better opportunity for me to master the language and the content. And so that's what we're seeing.
Thank you. We have one more. They are coming. Follow up to there not being many examples and Anne's question, what are the big challenges in enacting this approach more broadly in classrooms? And what are your thoughts on how to successfully navigate these challenges?
Such a simple and easy question there. Huh? Yeah, it's hard. It's difficult. So let me say this is high level teaching to ask a teacher to do this work. So let me start with the first idea. Identifying a context that is culturally meaningful for students means you have to relearn it for yourself, because none of us were taught this way. So I spent years figuring out, all right, I can teach chemical bonding by teaching hair care products, right? It took me to ask the question, but we first need to ask the question, what are the ways that we can teach these concepts so that it resonates with students in a powerful way? That's the first thing. So that means as a teacher, I have to really push myself pedagogically. All right, my pedagogical content knowledge has to really reshape for the kids I'm serving, because I've got to figure out where the science lives with them culturally. So the way that we teach it here, we really emphasize pre-assessments so that you can find out kind of what they know, more importantly, where they're learning these concepts. That's one thing. Secondly, is I'm asking teachers to do something new. And anytime I'm asking you teachers to do something new, the easiest way is a turnkey curriculum. That's not what I'm proposing. I'm proposing teachers learn to do this for themselves. And that's their big challenge. I hated professional development when I was a teacher, because it was always somebody telling me to do something new and more. And there was very rarely evidence that what they were suggesting would work better. So the one thing I can say is we do have that evidence, but I think the biggest challenge is compelling a group of people to take on a different type of practice because it requires effort and labor. And teachers are extremely busy already. And so that's, to me, are the biggest challenges. But my approach is to think through schools of education, the professional development groups, the people training the teachers, and that's probably the best impact that we can probably have.
Thank you. Does anybody who has asked a question, there's a new question here. Let me go to the new question first. The translanguaging practices also seem to promote effective, culturally sustaining practices, especially with teaching science in context using accessible language. Would you speak to how you view this intersection?
Yeah, so I think one of the things that is particularly challenging around translanguaging is you're really asking for two things to happen. Well, let me step back a step. I think we have to start with the assumption that we have monolingual teachers teaching multilingual students. Mm-hmm. So that is the heart of the challenge. So if I can't do the translanguaging, then what am I asking young people to do? I'm asking young people, those who are most fluent in both English and language, to be primary resources in small groups to do the translanguaging. I'm asking those who are uncomfortable. So let's start with the psychological positionality of my multilingual students who are learning English and have a Spanish resource. We want them to be able to use that resource. And so I have to create small group structures where I say, I value you using that language. I value using it to talk about culture, because what you are doing is learning. And so the challenge is I need to create small group structure. We follow the complex instruction model. from Rachel Lotan and oh my gosh, Elizabeth Cohen, where we put students in groups and everyone has a role. And if you do that, then you start to see multilingual exchanges where they value explanation because I've really given them the metacognitive platform. So let me say that simply. I want the students to know that part of what you need to do to become a master of this content is to explain it and explain it in both languages in order to get it. And if you do that, you create this richness in the classroom where students are able to work through it slowly. Now, I have a student, Dr. Greces Perez, who's at Tufts studying this right now. And so the early studies of this did not prove statistically significant improvement, but it also did not prove that there was any, it was a null result. So if you trans language and then students are using both languages, they were performing about the same. So there's some still work to do in this framework. But my primary message is imagine you're in an environment where they tell you your culture is not valued. Right? Don't use your language, don't talk about your home, right? There's no value here. We're saying the opposite. Use your own language, talk about the science that is happening in your own communities and see if that impacts learning. So it's a long answer for an efficient question, but the work is still happening.
Thank you. We do have 6 more minutes. I want to honor everybody's time, but everybody who asked a question, do you have any follow-up questions based on the responses that Dr. Brown provided? We didn't give opportunity for follow-up questions, but we do have a little bit of time to do that if anybody would like to follow up on the ideas that you were trying to explore in your question. Looks like not, maybe. What's the next in this area of research from Joel?
Well, that's a good question. So for us, we struggled. We could not convince NSF or NIH to fund kind of large scale, disaggregated instruction projects. We were too abstract, I guess. So we switched to technology. And so what we've been using for the last 5 years, I've been studying use of virtual reality and augmented reality and culturally relevant practices. And so the brief version is my computer in college couldn't compare to my iPhone. My iPhone is so much better than my computer. So it has AR, it has VR. I can run simulations on it. And so in a classroom environment, I can now have all 30 kids operating a simulation on their phone. Where there's power is that I can now have the person who's teaching them do that translanguaging. So the person that pops up in the virtual environment is speaking Spanish and speaking English. So I can diversify the technology much faster than I can diversify the teaching force. And so what we're working on is creating culturally relevant digital learning tools in science education. And so we have virtual reality projects. We just finished a sequence of what we call virtual field trips, where we're taking kids to Tanzania and they're learning about environmental restoration and biodiversity. But when they get there, they put the goggles on. It's, people of color, young people of color. They're taught by young people, young women of color in particular. There's hip hop music is the cue. They're sent messages of belonging and intentionally. And so that's what we're doing right now.
That is
a
very
really
exciting.
Clever way to use the technology. I love that example. And how are you getting that funded?
Well, Silicon Valley is funding us. So we've been different local foundations. We have a partnership with a number of startups. And so it's a variety of hodgepodge of funding sources at this point. If you're interested, if you go to our Science in the City website, it's scienceinthecity.stanford.edu. Some of those virtual reality lessons are there just for people to take a look at. You can download them and give them a shot if you're interested.
All right, folks, 3 more minutes. You have an opportunity to ask a question, make a comment, share a reaction.
Maybe I do have a follow-up since you brought it
Go
up
ahead,
on your
Ann.
website. So do you know that teachers are using this tool?
They're not. I mean, we have a group of teachers. I'm sorry. There's 10 teachers who kind of we co-design with this. So we design a lesson, give it to them, tell us it's terrible or try it. And so we have that working relationship. So that group, but No, people are not using it, partly because I want to make sure it's NGSS aligned
Yeah.
and it's functional. So we're not really at the point, we're not promoting any of it. Just
But
yet.
you will in the future, theoretically?
Absolutely.
Okay,
Absolutely.
awesome. Thank you.
Well, thank you very much, Dr. Brown, for your time and for sharing with us all the exciting work that you are doing. It's very inspiring to us. And as I had mentioned to you earlier, before the seminar formally began, we are using your book in our graduate program. And so it's great to see you and hear from you and interact with you during this past hour. Thank you so much.
Thank you. Thank you. Thank you. It's good to meet everyone. You all have a great day.
Yeah, you too. Thank you.
Brian.
We are adjourned. Thank you very much for coming, everybody.